Hey guys, so in this video we're going to begin a new chapter which is chapter 3 and the title is energy transfer and general energy analysis. So in this chapter we are going to understand energy um, in the thermodynamics field. Okay, how do we view energy in thermo? And after you've understood energy, we're going to see the methods of energy transfer, okay, how energy is transferred from one body to another. And lastly, we're going to do a general analysis of energy transfer. Okay, this last part will not be until the end of the week and will be continued until next week because this chapter is actually very crucial for you to understand the next chapter, chapter 4. Okay, so energy is commonly put as the symbol E. Okay, capital E, this is energy, and the unit is joules or kilojoules. Okay, and energy in simple terms is the ability to do work. So thermodynamics, however, deals only with the change of total energy. Okay, so we are not concerned with how much energy a substance uh, possess, but we are concerned with how the energy content changes after a certain process. Just like think of yourself. Okay, do you actually know how much energy you have right now? Okay, obviously the answer is no, because to calculate that, you need to calculate all the energy that the whole matter inside your body possess, which is very difficult to do. Okay, but instead, when you talk about energy, you know that you have gained energy when you have eaten a certain food, right? You can even check the energy content at the packaging of that food. And also, you know that you have lost energy whenever you have done some physical work, right? So, even in our daily life application, we also uh, analyze energy whenever there's a change in energy, but not the total content. Okay. Now the total energy here is including everything, which is thermal energy, mechanical, kinetic, potential, electric, magnetic, chemical, and nuclear. So this is pretty much all the energies that a substance can have. It does not necessarily have all of it, but these are the extent. Now, energy can generally be divided into two forms. Okay, so the two forms are macroscopic forms of energy and microscopic forms of energy. So by the definition of micro and macro, I think it's easy for you to remember the definition. Okay, macroscopic is when you are referring to some outside reference frame. So for example, kinetic energy, because only somebody, an observer from outside, can view kinetic energy. Also, potential energy. Ke is related to the motion of a system. If you remember, kinetic energy equals to half mv squared. So v, that is velocity, which represents movement. And potential energy, if you remember, is equal to mgh. So h is referring to the height. Okay, this contributes to potential energy. Now, for microscopic forms of energy, from the word micro, you know that it's not something that is visible to our naked eye. So these are energies related to the molecular structure of a system and the degree of molecular activity. So how much energy is between the molecules? What are the forces, attractive forces between the molecules and so on? Okay, so all these microscopic forms of energy, we simplify it and call it internal energy. Okay, so you might remember this, seeing this from your property table. Okay, all the property tables will have internal energy as one of the components because that is simplifying the microscopic energy. Because macroscopic we can easily calculate from the equations, but microscopic is impossible to calculate. Okay. Now, The total energy will then be summation of macro and micro. So macro you have Ke and Pe, micro you have U. Okay, so this is an equation that will follow you until the end of the semester. Okay, so please write this down, remember this. So let's look at some equations related to energy. Okay, so this is the general equation. So kinetic energy is half mv squared, and the unit is the same unit as energy, which is joule, or here in thermo we like to use kilojoules. Okay, because you find that most of the energy magnitudes are quite big, so we use kilojoules. And if you divide this equation by mass, okay, if you divide any property by mass, you remember, you get it in per unit mass form. So this will kilojoule, this will be kilojoule per kg. See that the m is gone, and the symbol for Ke will be small ke. Okay, small k, small e, small letters. So this is just like volume and specific volume, if you remember from chapter 2. Volume is capital V, specific volume is small v. Okay, not to be confused with the V here, which is velocity. Yeah, it's the exact same symbol. So it's up to you to understand it and not make the mistake. Now we have PE. So PE equals to mgz or mgh. This is height. Same thing, we can have the per unit mass form, just divide it by mass, and you have only gravity times height. And so this equation, the one that you've seen here, can be written as u plus mv squared over 2 plus mgz. So like I said, you can calculate these two terms, and u has to come from either experiment, which is not what we're going to do, or the property table. Okay, so per unit mass, if you divide the entire equation with mass, kilojoule here becomes kilojoule per kg, and all the terms just become small letters, and this will not have the mass term here. This one also will not have the mass term. Okay. So generally, you should know this from chapter 2. Any property can be divided by mass, and it will be the property per unit mass. Okay, why we have a lot of this is because when you're studying a system, you might not know the actual size of the system. By size, I mean how much substance is inside. Is it 1 kg? Is it 5 kg? So in order to make things simple, we have this flexibility of having something per unit mass. So if you have 10 uh, units of it, or 10 kg of it, then you just multiply the small e with 10 kg, and then you get the total energy. So this works with every property. Okay, so I've added here, recall the specific volume, the same concept. Okay, if you want to find the volume, you can just multiply the specific volume with whatever mass that you have. That will be the total volume. Okay, some physical insights to internal energy. This is additional. I'm not going to go into details. You can find the slide as usual in the chapter, in the week 3 folder. Yeah. So sensible energy is made of, internal energy is made of sensible energy, latent energy, chemical energy, and nuclear energy. Okay. Now, this is a system. And in the system, we have energy. So this could easily be you. Okay, your whole body here. And inside, there's energy. And this energy is called static energy. Imagine if you're not doing anything, okay, you have all the food inside your stomach and you're not doing any work, so it's static energy. Okay, and when the energy crosses your boundary, meaning that you are doing work right now, maybe you're moving, or if this is just another system, maybe the system is releasing some energy, this will be called dynamic energy. Okay, so dynamic energy is what we study. Alright, we deal with the energy as it crosses the boundaries. If it does not cross the boundary, we will not be able to analyze it. Okay, so the only two forms of energy interactions associated with closed system, right? So just like this is a closed system, the only way you can analyze this dynamic energy is through heat transfer and work. There's no other way you can study energy transfer. Okay, only heat transfer and work. So what is the difference between heat transfer and work? The answer is uh, an energy interaction is heat transfer when you have temperature difference. That means uh, from 10 degrees, it transfer heat to something that is lower temperature, maybe -2 degrees. So for sure there will be energy transfer. So that transfer is a heat transfer. Okay, if the energy is transferred by any other means, for example, a movement, expansion, then this will be considered as work. In the next video, we will go deeper into this heat transfer and work. So don't worry if you're not clear yet. So let's go through this example. A site evaluated for a wind farm is observed to have steady winds at a speed of 8.5 meters per second. So this is velocity. I hope you recognize the unit here. This is velocity. Determine the wind energy. Uh, there are three parts here. First, per unit mass. Remember, per kg. B is when you have a mass of 10 kilograms. And C, when you have a flow rate of air. Okay, this is something new for now. So first we can calculate for A. The wind energy per unit mass is simply, now how do I know to use this equation? Because the only energy that is happening when the wind is moving is kinetic energy. So kinetic energy is half mv squared. Since we want per unit mass, it's just v squared over 2 or half v squared. So v squared is this divided by 2. Conversion here is just showing that if you use velocity as meters per second, you will get the unit as joule per kg. Okay, I repeat, if you use energy ke per unit mass, the velocity here is meters per second, then it will automatically yield the unit of joule per kg. Okay, this is for kinetic energy. Next, when you have a mass of 10 kg, so what you do here is you just take the small e that you've calculated from up here times 10 kg. So the kg cancels each other out and you have 361 joules of energy. So energy is joules. So this is fine. The last one, you have kilograms per second. This is called mass flow rate. How much mass, how much air is flowing per second? So instead of the total amount of air, like in B, 10 kg of air, here you don't have the total, but you know how much air is moving per second. So to calculate, so you will see a new symbol here. Whenever you see this dot, it means this is per second. Yeah, energy per second. Energy unit is joule, so this is joule per second. You will see more of this in future videos, so don't worry. So instead of E equals ME, you have E dot to show that this is per second equals to, obviously the M will carry the dot because this is mass flow rate. It's kg per second of something times the E that you got from the first part. Okay, now there's a conversion of dividing the whole thing by 1000, because if you don't do this, you'll get the answer in watts. I hope you remember from previous subjects that watt is joule per second. In other words, this is power. Okay, so watt is joule per second, and how we get kilowatt is because we divide it by 1000. So we get kilowatts. So this is it for the introduction to energy. I see you in the next video.